we were discussing the laws of black body radiation, and last time when we stopped we had stated two laws, Planck's law for giving us the monochromatic emissive power of a black surface, and Wien's law which gives us the value of the wavelength at which the maximum value of the monochromatic emissive power occurs. Today we will take up the next law, the third law, that is the Stefan-Boltzmann law. The Stefan-Boltzmann law gives us the emissive power of a black surface. The Stefan-Boltzmann law is for the emissive power of a black surface. Planck's law has given us E b lambda. So, if I want to know what is the emissive power, what is the emissive power of a black surface, obviously I need to integrate E b lambda over all the wavelengths for which the radiation is being given off, and all the wavelengths are from 0 to infinity. So, the emissive power of a black surface E b is obviously nothing but the integral 0 to infinity E b lambda d lambda. All right. So, let us substitute Planck's law for E b lambda. If I substitute Planck's law, I will get 2 pi c 1 integral 0 to infinity 1 upon lambda to the power of 5 e to the power of c 2 by lambda t minus 1, the whole thing multiplied by d lambda. I have just substituted E b lambda from Planck's law into this expression. Now, we have to perform this integration. I am not going to do it here in the class, but what I am going to tell you is it is possible to perform this integration by expanding the E term, e to the c 2 by lambda t term, into a power series, into a series expansion, and then integrating term by term. If you do that, you will get a convergent series, you will get the result in the form of a convergent series which sums up to pi to the power of 4 into 90. So, the net result of doing this integration, which I am not doing here, but I am saying it can be done, it is not a very difficult integration, is to give you a final expression of the form 2 pi c 1, which is anyway there outside the integral, and the whole integral 0 to infinity, all this expression gives you 6 t to the power of 4 upon c 2 t to the power of 4 divided by pi to the power of 4 into 90. Now, all this is a constant, 2 pi c 1 is a constant which is given by Planck's law, 6 is a constant, c 2 to the power of 4 is a constant, pi to the power of 4 upon 90 is a constant. So, leave out T to the power of 4, which is the absolute temperature to the power of 4, and club all this remaining together into one constant, the rest of it. And what we get is therefore, this expression is equal to sigma into T to the power of 4, where sigma is all this 2 pi c 1 into 6 upon c 2 to the power of 4 into pi to the power of 4 upon 90. And sigma, if you substitute all the values, comes out to be 5.670 into 10 to the minus 8 watts per meter squared Kelvin to the power of 4. It is a constant with these values. So, the net result of the integration is to give us the emissive power of a black surface E b is equal to sigma t to the power of 4, and this is called the Stefan-Boltzmann law. All right. So, the Stefan-Boltzmann law, I repeat, is nothing but a law which is obtained by integrating Planck's law, which gives us an expression for E b lambda, integrating Planck's law over all wavelengths from 0 to infinity. The Stefan-Boltzmann law, after doing that integration, says E b is equal to sigma t to the power of 4, and sigma is a constant called the Stefan-Boltzmann constant, given by this value 5.67 into 10 to the minus 8 watts per meter squared Kelvin to the power of 4. So, we have three laws now for black body radiation: Planck's law, which gives us the monochromatic emissive power of a black surface; Wien's law, which gives you the wavelength at which the maximum value of the monochromatic emissive power occurs at a particular temperature; and Stefan-Boltzmann law, which gives you the emissive power of a black surface. Now, let us do a problem. The problem which we are going to do is the following. Let us do the following problem. Let us say we would like to find, the problem is concerned with finding the radiation given off from the sun. The temperature of the sun's surface, temperature of the sun's surface is 5779 Kelvin. All right, take this value as the temperature of the sun's surface, and the surface may be assumed to be black. The sun's surface may be assumed to be black. All right. We are required to calculate the values of lambda m, EB lambda at lambda equal to lambda m, and EB. All right, calculate these quantities using the laws which we have just stated. As calculate the values of lambda m, EB lambda at lambda equal to lambda m, and EB on the sun's surface. That is the problem. Also, determine EB lambda at lambda equal to lambda m and EB as received at the earth's surface. What are the values of these quantities as received at the earth's surface? All right, this is the problem. Now, we will take the following data for doing the problem. We will say take mean distance between the sun and the earth take the mean distance between the sun and the earth to be 1.496 into 10 to the power of 8 kilometers, okay, and take the radius of the sun to be equal to 0.695 multiplied by 10 to the power of 6 kilometers. These are values which are usually taken, the mean distance between the sun and the earth. The earth has an almost circular orbit around the sun. Take the mean distance to be 1.496 into 10 to the power of 8 kilometers. Take the radius of the sun to be 0.695 into 10 to the power of 6 kilometers. This is the problem. So, let us do it now. First of all, let us apply Wien's law. From Wien's law, what do we get the value of lambda m to be? lambda m multiplied by 5779, that is the temperature of the sun's surface. Wien's law says this is equal to 0.00290 meter Kelvin. Okay. Therefore, lambda m from Wien's law straight away comes out to be 0.5018 multiplied by 10 to the minus 6 meters, or if I multiply this by 10 to the power of 6, it is 0.5018 microns, micrometers. So, that is the value of lambda m. Now, let us apply Planck's law. From Planck's law, we will get the value of E b lambda, and we want it at lambda equal to lambda m. So, let us put that value, this value of lambda m which we have just found out. So, now let us apply Planck's law to get E b lambda at lambda equal to lambda m. So, we get from Planck's law E b lambda at lambda equal to lambda m is equal to 2 pi C1, 2 pi multiplied by C1 0.596 to 10 to the minus 16, this is the constant C1, divided by the lambda to the power of 5, divided by lambda to the power of 5, let us put that 0.5018 into 10 to the minus 6, the whole thing to the power of 5 into exponential of C2 by lambda t, C2 is 0.014387, lambda t will be 0.00290, all right, minus 1 and close the bracket. Okay. That is equal to, that will come out equal to, on doing the calculation, we will get this is equal to 0.83038 into 10 to the 14 watts per meter cube, or if you want to express it in the units which we usually do, 8308 into 10 to the power of 8 watts per meter squared micron. This is the unit usually used for E b lambda. So, this is the next value which we are looking for, the value of E b lambda at lambda equal to lambda max. Now, let us get the value of E b rather. So, we will get from the Stefan-Boltzmann law, from I will write just S b law, E b is equal to sigma 5.670 into 10 to the minus 8 multiplied by 5779 to the power of 4, t to the power of 4 where t is in absolute Kelvin, all right, is equal to, that comes out equal to 63.24 multiplied by 10 to the power of 6 watts per meter squared. So, that is the value of E b. This is the first part of the problem. Now, the next part is you are asked also to find the values of E b lambda at lambda equal to lambda m and E b at the earth's surface. Okay. So, that is the next part. Now, mind you, you should note what is happening to the radiation which comes out from the sun. Suppose let us say this is the sun, let me just draw the sun here, let us say this is the sun, all right. The radiation from the sun is going out like this in all directions spherically, all right. That is how the radiation from the sun is going out, isn't it? And let us say this is the earth here, Okay. We are told that the average distance between the sun and the earth, the average distance, let us put that down, between the sun and the earth is 1.496 average distance 1.496 into 10 to the 8 kilometers. This is the earth, this is the sun, and the radius of the sun is 0.695. This is the radius of the sun. .695 into 10 to the 6 kilometers. 695 into 10 to the 6 kilometers. This is the geometry we are dealing with. We have the value of E b lambda and E b at the sun's surface, that is right here where I am showing it. Okay. We want the value at this point, that is at the earth's surface. Now, mind you, I am not distinguishing between the earth's surface and the center of the earth, because the radius of the earth is so small, there is no point in worrying about that here, because of the distances, the other distances involved. All right. So, we have a value of E b lambda and E b out here. We want the value here. Now, the radiation coming out from the sun is going out spherically in all directions. So, obviously, it is going to be, the flux is going to be inversely proportional to the square of the distance, because the surface area of a sphere is 4 pi r squared, right. Therefore, E b lambda, we can straight away say E b lambda, lambda equal to lambda max at the earth's surface, on the earth's surface, it's inversely, the value will be inversely proportional to the square of the radius. So, it is simply going to be equal to the value that we got previously, 0.83038 multiplied by 10 to the power of 8, all right. This is so many watts per meter squared micron, multiplied by the radius of the sun, 0.695 into 10 to the 6, divided by the distance between the sun and the earth, which is 1.496 into 10 to the 8, and the square of this, because it is inversely proportional to the square, and that will come out to be 1792 watts per meter squared micron. So, from Planck's law, if I take the average temperature of the sun's surface to be 5779, the value of the maximum value of the monochromatic emissive power at the earth's surface is 1792 watts per meter squared micron. Similarly, the value of E b on the earth's surface will be given by 63.24 into 10 to the 6, that is the value on the sun's surface, multiplied by 0.695 into 10 to the 6, divided by 1.496 into 10 to the 8, the whole thing squared, all right, and that will come out to be, if you calculate it, you will get the value to be, that is equal to 1365 watts per meter squared. So, that is the flux received at the earth's surface, E b as received at the earth's surface emitted from the sun. This particular quantity is in fact called the solar constant. This is called the solar constant. Okay. So, here is a simple problem which we have done to illustrate how to use all the laws of black body radiation, Planck's law, Wien's law as well as the Stefan-Boltzmann law. Okay. Now, if all these laws give you values for black surfaces, but as an engineer we are dealing with real surfaces. Real surfaces are not black surfaces, all right. They have emissivities, some value of emissivity, and for a real surface you know E is equal to, the value of E is equal to, for a real surface, the value of the emissive power is the emissivity into the value E b, which is for a black surface. So, E b I will get from the Stefan-Boltzmann law, but epsilon, the emissivity of the surface, I need to know, that is a property of the surface, all right. So, just like when we did calculations in conduction, you need to know the value of thermal conductivity K everywhere. Similarly, in radiation, if you want to know how much is going to be radiated from a surface which is at a given temperature, you need to know the emissivity of that surface. So, there is a lot of data available in the literature, measurements made by various investigators over the years, which give us values of emissivity for all kinds of surfaces that we use in practice. Now, let us look at a few such values. I am going to show you some values of emissivity for some common surfaces, just to give you a feel for the numbers that are involved. So, here is a table showing the emissivity of some common surfaces, all right, a table showing the emissivity of some common surfaces, the emissivity of some common surfaces. I have grouped the matter into three things, that is, first I am going to talk about the emissivity of metal surfaces, then the emissivity of non-metal surfaces, then the emissivity of liquid surfaces, all right, one by one. So, let us look at the first, the emissivity of, and let me just blank off the other, so that your attention stays only on the first part. Let us focus our attention first on the emissivity of metallic surfaces. Okay. I have picked three here as an example. Which are the three? Brass, copper, steel, and in each case I have distinguished between polished surfaces and oxidized surfaces, polished, oxidized, polished, heavily oxidized, and for steel I have also talked of commercial surfaces. Okay. Now, notice the emissivity for a polished surface, polished brass surface as measured 0.09, polished copper surface 0.04 to 0.05, a polished steel surface 0.08 to 0.14. Okay. So, notice that when you have a polished metallic surface, the value of emissivity is quite low, it has to be between 0 and 1, it is quite low, usually less than 0.1, 0.09, 0.04, 0.08 are typical values. The moment the surface is oxidized, the value goes above 0.5. Look at oxidized brass 0.6, look at oxidized copper 0.5 to 0.8, look at heavily oxidized steel 0.81. So, the moment I have an oxidized metallic surface, the value will usually be greater than 0.5, maybe 0.6, 0.7, 0.8, something like that. So, this is a rough thumb rule to remember. A polished metallic surface may have an emissivity of the order of 0.1 or less. An oxidized metallic surface would typically have values greater than 0.5, 0.6, 0.7, something of that order. That is one comment. If you really want, of course, to have precise values, you need to go to a handbook. These are just some rough indicators of the type of values we get. Now, let us look at the next class, that is, I have put down the emissivities of some non-metals. All right. Here are some emissivities of non-metals: brick, concrete, glass, oil paints, wood, a variety of non-metallic surfaces. And look at the emissivity values: brick 0.93 to 0.96, concrete 0.88 to 0.94, glass 0.90 to 0.95, oil paints 0.92 to 0.96, wood 0.94. So, typically a non-metallic surface would typically have a value greater than 0.8, more like 0.9 in most cases. Keep that in mind. A non-metallic surface usually has an emissivity of the order of 0.9, 0.8, 0.95, something like that. So, that is a second comment, comment about emissivity values. Again I repeat, you want precise values, you need to go to handbooks, because emissivity will also be a function of temperature. Here I have given the value at a particular temperature. It will be a weak function of temperature, not varying that strongly, but nevertheless a function of temperature. And finally, I have given the value for one liquid surface, and that is water. Notice, for water, the emissivity value at room temperature, that is about 300 K, the value is 0.95. Water has an emissivity of 0.95 at a room temperature of about 300 K. This is true of most liquid surfaces. The emissivity values will be around 0.9, 0.95 for most liquid surfaces. So, I want you to keep these magnitudes of emissivity in mind when you do approximate calculations in radiation. Exact values, of course, can always be obtained from the handbooks which are available, in which measurements made by various investigators are tabulated. All right. Now, we have talked about the emission characteristics of surfaces, right. We have talked about, first of all, defined terms like the total hemispherical emissive power, or what we call only as emissive power, the monochromatic emissive power, the emissivity of a surface, the monochromatic emissivity of a surface, and we have also stated the three laws for black body radiation. This is all concerned with radiation being emitted from a surface which is at a particular temperature. Now, we want to talk about radiation falling on a surface, that is, radiation incident on a surface. Okay. Let us now talk about radiation incident on a surface. This radiation which we are talking about may have come from some surrounding surface. It may have been emitted by some surface and then is falling on the surface with which we are concerned. So, the radiation falling on a surface has originated from probably from some other surface from which it is being emitted. Okay. Now, when radiation falls on a surface, a part of that radiation is absorbed and the rest is reflected. If the body is transparent, a part may also be transmitted. So, three things happen to radiation when it falls on a surface, when it is incident on a surface. A part of that radiation is absorbed, a part of it may be reflected, and a part may be transmitted through that body, if that body is transparent to radiation. Say for instance, light is falling on a glass, then some of the light may go through the glass. This is shown pictorially in this figure here, where I have drawn a rectangular block and said some ray of radiation is falling. I have shown just one ray, not radiation coming from all directions. Just for as an example, I have shown one incident ray coming here, and I have said what will happen to it? It will be reflected, it will be part of it will be absorbed, and a part will be transmitted. Three things will happen: reflection, absorption, and transmission. A part will be reflected, part will be absorbed, and the remaining may be transmitted. Or if it is opaque to radiation, then it will only be reflected and absorbed. Now, the reflection itself can be of two types. All right. One is the reflection may be like we have when light falls on a mirror, for instance, typically optical light falls on a mirror, the angle of incidence is equal to the angle of reflection. You follow? So, reflection may be of that type in one direction with the angle of incidence equal to the angle of reflection, or reflection may be in all directions as is shown by all these arrows here going outwards. That means, reflection is in all directions. You understand? So, generally for surfaces that we deal with in real life, when thermal radiation falls on a surface, any ray, it may be coming from one direction or from all directions, but any particular ray which comes and falls on a surface will normally be reflected in all directions, not following this rule of the angle of incidence being equal to the angle of reflection. So, keep in mind, reflection in all directions is the thing that generally occurs. Okay. So, we are now talking about what defining, we are going to define some terms concerned with radiation incident on a surface. The first term which we are going to define is the following. We define a term called the total hemispherical irradiation, H. Okay. We define it as the radiant flux incident on the surface of a body. The units of it would be in watts per meter squared. The total hemispherical irradiation is the radiant flux incident on the surface of a body. Now, let me illustrate this with a sketch again. Let us say this is a some surface like this, and let us say radiation is incident on it from some surrounding surfaces, radiation emitted by surrounding surfaces is incident on this surface coming from all directions like this. All right, this is radiation incident on a surface. And let us look at an area here on this surface, some area here on which the radiation is incident. Okay. Now, the total hemispherical irradiation, I have said to you, is the radiant flux incident on the surface of the body in watts per meter squared. The word total which I use stands for all wavelengths. That is what we mean by total, something summed over all wavelengths, 0 to infinity. And the word hemispherical includes all directions within a hemisphere. That is what we mean by the words total and hemispherical. So, total hemispherical irradiation, H, is the radiant flux incident on the surface of a body, so many watts per meter squared. Now, I have already told you a fraction of this may be absorbed. Okay. Let us say the fraction of this irradiation absorbed at the surface is alpha. We call alpha as the total hemispherical absorptivity of the surface. All right. Alpha, the total hemispherical absorptivity, is the fraction of the total hemispherical irradiation absorbed at the surface. Let us say the absorbed flux is H A, the incident flux is H and the absorbed flux is H A. So, alpha is nothing but H A upon H. All right. H A is the absorbed flux. Both are in watts per meter squared. And obviously, for a black surface, by definition, a black surface is 1 for which alpha is equal to 1. A black surface has the absorptivity, the total hemispherical absorptivity equal to unity. So, we have defined two terms, H, the total hemispherical irradiation which is incident on a surface, and alpha which is the total hemispherical absorptivity of the surface. We have defined two terms. Now, let us define two analogous terms for monochromatic irradiation. Next two terms we are going to define are concerned with monochromatic irradiation. We say monochromatic hemispherical irradiation, we will use the symbol H lambda for it, monochromatic hemispherical irradiation, we use the symbol H lambda for it, is the radiant flux incident on the surface of a body per unit wavelength, and it will have the units of watts per meter squared micron. So, H lambda is nothing but dH d lambda, the watts per square meter per unit wavelength, dH d lambda, or we can say dH is nothing but H lambda d lambda. If I integrate H lambda over all wavelengths, then I have got to get the quantity H. So, another way of defining H lambda is to say it is that quantity, H lambda is that quantity which when integrated over all wavelengths 0 to infinity will give me the total hemispherical irradiation on the surface. So, we can say, let me repeat, the monochromatic hemispherical irradiation on a surface H lambda is that quantity which when integrated over all wavelengths ranging from 0 to infinity gives us the total hemispherical irradiation H incident on the surface. So, that is another way of looking at the quantity H lambda. And we define the last term now. The last term will be the monochromatic hemispherical absorptivity of a surface, for which we will use the symbol alpha lambda, monochromatic hemispherical absorptivity of a surface alpha lambda, and we say it is the fraction of the monochromatic hemispherical irradiation absorbed at a surface. Out of the quantity H lambda, a certain amount is absorbed, let that be H A lambda. The ratio H A lambda by H lambda is the fraction that is absorbed of the monochromatic hemispherical irradiation, and we will denote that by the symbol alpha lambda. So, alpha lambda is H A lambda upon H lambda. H A lambda is the absorbed monochromatic hemispherical irradiation. Obviously, again for a black surface alpha lambda is equal to 1. All right. So, there is irradiation falling on a surface, H if it is all the radiation, H lambda if it is the monochromatic value that you are looking for, a certain fraction out of it is absorbed. In the first case, the fraction absorbed we call as the total hemispherical absorptivity, denoted by the symbol alpha. In the second case, when it is monochromatic, we call it the monochromatic hemispherical absorptivity and denote it by the symbol alpha lambda. In the same manner, exactly in an analogous manner, I can define terms like total hemispherical reflectivity and monochromatic hemispherical reflectivity. These would be rho and rho lambda, and I can define terms like total hemispherical transmissivity and monochromatic hemispherical transmissivity, which would be tau and tau lambda. You understand? What would be rho? Rho would be the fraction of the total hemispherical irradiation incident on a surface which is reflected from the surface. And what would be tau? Tau would be the fraction of the total hemispherical irradiation incident on a surface which is transmitted through that surface. Okay. So, rho and tau are similar to alpha. Alpha stands for the absorbed fraction, rho for the reflected fraction, tau for the transmitted fraction, and the corresponding quantities in monochromatic level are alpha lambda, rho lambda, tau lambda. Okay. Therefore, it follows from the definitions, it follows that alpha plus rho plus tau must be equal to 1, alpha lambda plus rho lambda plus tau lambda must also be equal to 1. That follows from the definitions, because only three things can happen to the radiation. It can be absorbed, it can be reflected, or it can be transmitted, and the sum of the three fractions has to add up to 1. For all the incident radiation, these three things can happen. So, alpha plus rho plus tau is 1, alpha lambda plus rho lambda plus tau lambda must be equal to 1. And if the body is opaque, like for instance it is a metallic surface, say for instance, so that no radiation can go through the surface. Then if the body is opaque, tau and tau lambda would be 0, and then alpha plus rho is equal to 1, and alpha lambda plus rho lambda is also equal to 1. So, instead of the first two expressions here, I get these two expressions if the surface of the body, if the body is opaque and no radiation is transmitted through it. And this is very true very often, because we deal very often with metallic surfaces. So, no radiation goes through, and alpha plus rho is equal to 1, alpha lambda plus rho lambda is then equal to 1. Okay. Now, let me just sort of put things together just to recapitulate again once more what we have said. We have now defined the following quantities. I am just sort of repeating things a little. I am saying, let me make a table. So, I will say first total hemispherical, and monochromatic hemispherical. We have defined two types of quantities, monochromatic hemispherical, all right. Total hemispherical emissivity we have defined for radiation which is emitted from a surface, all right. And total hemispherical emissivity we have epsilon. If it is the monochromatic value, we have defined epsilon lambda. Then this is with respect to emitted radiation. Then with respect to irradiation, we have defined three quantities: absorptivity, then reflectivity, and transmissivity, which we call as alpha, rho, tau, alpha lambda, rho lambda, tau lambda. So, these are all properties that we have for the surface. Okay. The last three are for irradiation, that is radiation incident on a surface. These are for irradiation. The first one is for emission. So, these are all, this is kind of a snapshot of the terms we have defined. And also I repeat that we have also got the same abbreviated versions that we had earlier. That means, we will use the same abbreviations earlier. We will not keep on saying things like instead of saying total hemispherical irradiation, instead of going on saying this every time, we will, which is the quantity H, all right, we will normally delete the words total and hemispherical and refer to it only as irradiation, in the same way that we did that earlier for emissive power. Similarly, the quantity total hemispherical absorptivity, which is alpha, we will simply call it as absorptivity. By deleting the words total and hemispherical, they are implied. Or when we will not keep on saying monochromatic hemispherical irradiation, which is H lambda, we will simply call it monochromatic irradiation. we will simply call it monochromatic irradiation, deleting the word hemispherical. And finally, in the same vein, we will not use the phrase monochromatic hemispherical absorptivity, that is alpha lambda, all right. We will delete the word hemispherical and simply call it monochromatic absorptivity. Simply call it monochromatic absorptivity. Okay. And also, like earlier, we will instead of monochromatic, sometimes following other authors, we will use the word specular instead of monochromatic and call it specular irradiation or specular absorptivity instead of monochromatic absorptivity. You should know these different terms that are used by various people. Many people, instead of calling it monochromatic absorptivity, call it as specular absorptivity. So, I want you to know these terms. Now, let us do one more problem again, so that these ideas get illustrated about these terms, absorptivity, monochromatic absorptivity, etc. So, let us do the following problem. The problem we want to do is like this. We say, let us say I have a surface. For a surface, the variation of monochromatic irradiation, of monochromatic irradiation, that is H lambda, on an opaque surface and the variation of the monochromatic irradiation on an opaque surface and the monochromatic absorptivity that is alpha lambda with wavelength is as shown. For a given surface, this is the variation, some variation which I am going to show now. It's like this. Let us say one for alpha lambda, the other for H lambda. This is lambda on the x axis. Let us say this is lambda and this is 0 microns, 2, 4, 6 and 8 microns. Okay. Now, the variation of H lambda is given to be the following. You are told that H lambda for this surface is like this. It is a simple rectangle like this for the surface. This is H lambda in watts per meter squared micron and the value is 750. All right. So, it is 750, the value is 750 from 2 to 8 microns, otherwise it is 0. And the alpha lambda varies from like this, 1 comes down to 0.5, then is 0.5, then is 0. So, the variation of alpha lambda is, this is 1, this is 0.5. So, alpha lambda is 1 from 0 to 4 microns and 0.5 from 4 to 8 microns, thereafter it is 0. Okay. So, this is the variation which is given. Find, calculate absorbed radiant flux that is H A, calculate the absorptivity that is alpha and calculate the reflectivity that is rho. Okay. Now, what are they? Very easy to find out. H A, the absorbed radiant flux, is the integral 0 to infinity H A lambda d lambda, that will be the absorbed radiant flux. So, that is nothing but the integral 0 to infinity alpha lambda H lambda d lambda, all right, where H lambda is the incident flux. That is nothing but, now let us do it in steps. Let us take it first from integral 0 to 2 microns and put a value of H lambda from 0 to 2 and put the value of alpha lambda from 0 to 2, which is 1, plus integral 2 to 4, value of alpha lambda is again 1, since it is constant I can take it outside the integral, multiplied again by H lambda d lambda, plus the integral from 4 to 8, alpha lambda is 0.5, H lambda d lambda, and finally, the last one 8 to infinity 0, and that is to be multiplied by H lambda d lambda, all right. So, we will get 1 multiplied by 750 into 2, the first integral, plus the first is 0 of course, the second one gives me 1 into 750 into 2, the third one gives me 0.5 into 750 into 4, and the last one also is 0. Okay. So, these two go away, the first and the last are both obviously zeros, because here H lambda is 0 and here alpha lambda is 0. The second and the third give me these values, and if I calculate them, I get nothing but 1500 plus 1000, which is 3000 watts per meter square. That is the value of H A. So, therefore, what is alpha? Alpha is nothing but 3000 divided by the incident radiation. The incident radiation you know is nothing but 4500, 750 into 6, and therefore, alpha is 0.667, and it follows that because the surface is opaque, it follows therefore, that rho must be equal to 1 minus 0.667, that is it must be 0.333. So, you see here is a very simple problem in which we have illustrated the ideas of all these quantities which we have defined today, namely the absorptivity, the reflectivity of a surface. Now, today we have completed how to deal with radiation which is coming from all directions, that is hemispherical radiation. Next time we look at the direct nature of radiation.